Hello everyone, welcome to my YouTube channel, and today we are going to discuss some of the sample question of the data science course. First question is, explain how unstructured data is transformed into a format suitable for machine learning model. Summarize the importance of legal classification in the context of grievance redressal, how TF-IDF or word embedding can be used to extract features from complaint text. Solution of the question is transforming unstructured data into a format suitable for machine learning models. Unstructured data, such as text or images, does not have a predefined model or structure, making it difficult to process directly for machine learning. The process of transforming this data into a format suitable for machine learning typically involves the following steps. First, data processing. Text cleaning. This involves removing unnecessary elements like punctuation, special characters, stop words, and numbers that may not add value to the analysis. Tokenization. The text is broken down into smaller units such as words, phrases, sentences known as tokens. Normalization. This step involves converting all tokens into a consistent format, example lowercasing all words or removing extra spaces. Feature extraction. Vectorization. Text data is converted into numerical representation that machine learning models can understand. Common methods include TF-IDF, term frequency, inverse document frequency, a statistical measure used to evaluate the importance of a word in a document relative to a collection of documents. Word embeddings. These models map words to high-dimensional vectors in a continuous vector space, capturing semantic meaningful and relationship between words. Dimensionality reduction. If the feature space is too large, methods like PCA can be used to reduce the number of features while preserving the core information. Data splitting. Once features are extracted, the dataset is split into training and testing sets to evaluate the model's performance. Importance of legal classification in grievance redressal. Legal classification in grievance redressal refers to categorizing complaints or grievances according to legal categories or relevant laws. This is important for several reasons, and the reasons are efficient handling. It helps in directing grievances to the appropriate department or authority. For example, a complaint related to consumer rights should be directed to consumer protection authorities, whereas labor related complaints should go to the labor department. Timely resolution. By classifying the complaint based on legal parameters, the resolution process becomes more efficient and timely, ensuring that the legal aspects are considered appropriately. Accuracy and accountability. Proper classification ensures that complaints are dealt with according to the specific legal provisions, reducing the chances of errors or inappropriate handling, and making authorities accountable for resolving the issue in line with legal frameworks. Data analysis. With proper classification, trends and patterns in complaints can be analyzed to identify systematic issues, allowing authorities to address root cause and improve governance. Using TF, IDF, or word embedding to extract features for complaint text. TF IDF is a technique used to convert text data into a numerical form. It calculates two components for each word, term frequency and inverse document frequency. Term, term frequency, that is TF, measures how frequently a word appears in a document, and TDF measures how important a word is across all documents. Words that appear in many documents will have a lower IDF value, while rare words will have a higher IDF value. When applied to complaint text, TF-IDF can highlight important words while downplaying common words, creating a weighted representation of the text that is useful for identifying patterns and classifying complaints. Word embeddings such as word2vec or glob represent words in a dense continuous vector space where semantically similar words are mapped close to each other. In context of grievance redressal, word embeddings can capture the meaning behind word in complaints. For example, words like refund, compensation, and return might be close to each other in the embedding space, indicating that they share a similar meaning in the context of consumer complaints. Word embedding are particularly effective for capturing context and handling synonyms, which can be challenging with methods like TF-IDF. Both TF-IDF are and word embeddings are used to extract features from complaint text, but the choice between the two depends on the nature of the problem. TF-IDF works well for identifying specific important words, while word embedding are better suited for understanding the contextual meaning of words. Second question is explain the role of text mining in automating grievance redressal system. List the key steps involved in pre-processing unstructured text data. Role of text mining in automating grievance redressal system. Text mining plays a crucial role in automating grievance redressal system by transforming unstructured complaint data into structured, actionable insight. Grievances, complaints, and feedback from customers or citizens often come in textual form, and text mining enables extraction of valuable information from these texts to streamline and automate the process of handling grievances. Key roles of text mining in grievance redressal system include automated classification. Text mining techniques can be used to classify grievances automatically into predefined categories. This ensures that the complaint is routed to the appropriate department or person for resolution. Second, sentiment analysis. Text mining helps identify the sentiments behind a complaint. Example, positive, negative, neutral. Sentiments analysis can prioritize complaints based on urgency or severity, helping the system to handle high priority cases first. Topic modeling. Text mining algorithm like latent direct allocation can uncover the main topics or themes in a collection of complaints. This helps in identifying recurring issues, enabling proactive measures to prevent similar complaints in the future. Named entity recognition. NER techniques identify specific entities such as names, dates, and location in the text. This is helpful for extracting critical information like the subject of the complaint and linking the complaint to relevant legal or operational processes. Text summarization. Text mining can be used to summarize long complaint text into concise, relevant piece of information, making it easier for the grievance redressal system to process and respond quickly. Automating responses. By applying text mining to analyze historical complaints and resolution, the system can generate automated responses or solution based on similar past cases, improving the efficiency of the redressal processes. Trend and pattern analysis. Text mining helps to detect trend and pattern in grievance data, such as frequent complaints about a specific product or service. This can guide the company or authorities in improving their services or addressing systematic issues. Key steps involved in pre-processing unstructured text data. Pre-processing is an essential step in transforming raw, unstructured text data into a structured format that can be used by machine learning models. The key steps involved are text cleaning, tokenization. Text cleaning involves removing noise, lowercasing, removing stop words, removing numbers or special character. Basically, removing noise means removing special symbols or special character in the data. Lowercasing all the words. If something written in the uppercase, that should also be done in the lowercase. Removing stop words. Stop words means is than. These words are called as stop word. So removing these words, removing number or special character. The numbers or the special character used in the data or the text should be removed. Tokenization involves splitting text into smaller units such as words, phrases, or sentences. This helps break down the text into manageable parts for further processing. Stemming and lemmatization. Stemming reduces words to their root form. Lemmatization is similar to the stemming but more accurate as it reduces words to their base or dictionary. Both techniques help in reducing variations of a word to a single form, making it easier to analyze. Removing rare or frequent words. Words that appear too frequently, like is, than, the. These stop words appear too many times in the text data. So removing them. makes the analysis easier. Part of speech. Identify the grammatical structure of the sentence. This step helps in understanding the role of each word in the text and can be useful for more advanced NLP tasks like named entity recognition. Vectorization. After text has been cleaned or tokenized, it is converted into numerical vectors that machine learning models can understand. Techniques like TF-IDF or word embeddings can be used for this step, converting the text into vectors of fixed length that capture the semantic meaning of words. Removing duplicates. Identifying and removing duplicate complaints or identical entries in the datasheet ensure that the analysis is based on the unique data points. Handling missing values. If some complaints have missing information, imputation techniques or removal of these entries might be needed. By following this reprocessing step, the unstructured grievance data is transformed into a clean, structured format suitable for analysis and machine learning application. Now, next question. Explain the concept of linear regression, how the best fit is determined. Linear regression is a simple and useful tool for predicting a quantitative response. The relationship between input variable and output variable y takes the form y was to be beta 0 plus beta 1 x1. Here beta is the coefficient. Beta 0 to beta p are the unknown coefficients which we are trying to determine. The best coefficient will lead to the best fit, which can be found by minimizing the residual sum squares or the sum of the differences between the actual ith value and how to find best fit.
How to
The
find
input data
best
and
fit.
y represent the
The
output
input
data.
data and y
This
represent
method
the
is used
output
for
data.
smaller
This
matrices
method is
since
used for
converting
smaller
a matrix is
matrices since
computationally
converting a
expensive.
matrix is
Gradient
computationally
descent first
expensive.
order
Gradient
optimization
descent first
algorithm.
order
We
optimization
can find
algorithm. We
the
can
minimum
find
of a convex function
the minimum of a convex function
by starting at an arbitrary point
by
and
starting at
repeatedly
an
take
arbitrary
steps in
point
the downward
and
direction
repeatedly
which
take
can be
steps
found
in
by
the downward
taking the
direction
negative
which can be
direction
found by
of
taking
the
the
gradient.
negative direction
After several
of the
iterations, we
gradient.
will eventually
After several
converge to the
iterations, we will
minimum.
eventually
In
converge
our
to the
case, the minimum
minimum.
corresponds to the
In our case,
coefficient
the
with the
minimum
minimum error
corresponds to the
or the
coefficient with
best
the
line
minimum
of
error
fit. The
or the
learning
best
rate
line
alpha
of fit.
determines the
The
size of
learning
the
rate
steps we
alpha
take in
determines the
downward
size of the
direction.
steps we take
Next
in downward
question,
direction.
question number 4.
Next
That
question.
is,
Question number 4.
write
That
an
is,
algorithm to create two clusters
write an
from the
algorithm to
set
create two
given, write
clusters
output of
from the set given.
each
Write
10 round.
output of
To create two
each 10
clusters
round.
from the given set,
To create
we
two
can use
clusters
the
from the
k-mean
given
clustering
set, we can
algorithm,
use the
which
k-mean
is a widely
clustering
used
algorithm,
method for
which
clustering.
is a
This
widely
algorithm
used
works
method
by
for
partitioning
clustering.
the
This
data
algorithm
into
works
k
by
clusters.
partitioning
In
the
this case,
data
k
into
equals
k
to 2.
clusters. In this
The
case,
k-means
k equals
algorithm
to 2.
follows these basic
The
steps.
k-means algorithm
First step
follows
is
these basic
initialize
steps.
centers.
First
Randomly
step
select
is
k points
initialize
as the
centers.
initial
Randomly
centroid.
select k
From
points
this
as the
set, the
initial
given
centroid.
set 2, 4,
From
10,
this set,
20,
the given set
20,
2,
30,
4, 10,
11 and
12,
25.
20,
From this
30,
number,
11 and 25. From this
any
number,
two k points are
any
selected, any value,
two k points
2
are selected,
or
any
30,
value, like
4 or
2
11,
or
2 or
30,
4,
4 or
like this.
11,
Any of
2
the
or
values
4,
is
like
selected.
this. Any of the values is
Assign
selected.
points to nearest centroids.
Assign points to
Distance
nearest centroids.
from the point we
Distance
selected as k
from the point we
and
selected as k,
distance of
and
those points k
distance
is
of those
determined
points
from
k
all the other
is
remaining
determined
points.
from all the
For
other
each point in the
remaining
dataset,
points.
assign it to
For
the
each
nearest
point in the
centroid
dataset,
based on
assign it to the
Euclidean
nearest
distance.
centroid based on
And
Euclidean
the
distance.
point which is nearest
And
is
the point
grouped
which
with
is
the
nearest is
point
grouped with the
that we initialize
point
as k.
that
Update
we
centroid.
initializes
Compute
as
the
k.
new centroid
Update
to the
centroid.
cluster formed in
Compute the
step
new
2.
centroid of the
Keep it
cluster
step 2
formed
and
in
3
step 2.
the
Keep it
centroids
step
do
2 and
not
3
change
enter.
significantly
The
or the
centroids
set
do
of
not change
numbers of
significantly
iteration
or
is
the set of
reached.
numbers of
I
iteration
will
is
walk through
reached.
each of the 10
I
rounds
will
of the
walk
algorithm for
through
this
each of the
dataset
10
where the
rounds of the
initial
algorithm for this
centroids are
dataset
randomly
where the
selected
initial
and
centroids
updated
are
over 10
randomly
iterations.
selected and updated over 10
First step is
iterations.
initialization. So k
First
is
step
equals
is
to 2.
initialization. So k is equals to 2.
Randomly we initialize the
Randomly we
centroids.
initialize
Let's
the
assume the initial
centroids.
centroids
Let's
are 2
assume
and
the
20.
initial centroids are
So
2
in
and
first
20.
round, assign points to
So
the
in
closest
first round,
centroid,
assign
distance of
points to the
centroid.
closest centroid,
Now,
distance of
the
centroid.
distance of each
Now,
remaining
the distance of each remaining point,
these two initial
from
centroid, that is 2
these
and
two
20 is
initial centroid,
calculated,
that is 2 and 20 is
according to the
calculated,
nearest distance,
and
they are
according to
grouped.
the nearest
So here the
distance they are
distance
grouped.
from
So
each
here the distance from each
point k is calculated,
point
and
k
then
is calculated,
from the distance
and then
from the
from the
centroid to that is
distance
20.
from the
From
centroid to
20
that
the
is 20.
distance is
From
calculated.
20 the distance
Now
is calculated.
the
Now
according to the
these
distance,
the
according to the least
according to
distance
the
from the
distance
point.
according to
The
the
point
least
which is
distance
nearer
from
to
the
the
point,
centroid
the
2
point
and
which
the
is nearer
point
to
which
the
are nearest to
centroid
the
2
centroid
and the
20.
point which are nearest
Grouping
to the
is done.
centroid
Like
20.
2, 4, 2
Grouping
are
is
nearest to
done.
the
Like
centroid
2
2
4 2 are
and
nearest to
all
the
the
centroid
remaining
2, and
points 10,
all the
12,
remaining
20, 30, 11,
points 10
25 are
12 20 30
nearer
11
to
25
the
are
20.
nearest to the 20.
Now recalculate the centroids. New
Now
centroids
recalculate the
are,
centroids. New
this
centroids
is
are, this
2
is
plus 4 plus 2 by
2
3
plus
and
4 plus
this
2 by
calculation is
3,
done in
and
round
this
2.
calculation is
Now
done in round 2.
another 2
Now
centroids are
another 2
taken.
centroids are
Assign
taken.
points to the closest centroid.
Assign
Distance
points
to
to the
centroid 1.
closest centroid. Distance to
Now
centroid
this
1.
distance,
Now
that
this distance,
2.67
that
is
2.67
the result of
is
first
the
centroid.
result of
Now
first
that distance
centroid.
is calculated
Now
from
that
all the
distance
other
is
points,
calculated from all the other points,
and similarly
and similarly
18, that is the result of second
18,
centroid,
that is the
20.
result of second
distance
centroid,
of
that is 20. The distance of
this centroid, centroid 2
this
is calculated
centroid,
from all the
centroid 2
remaining
is
points,
calculated from all the
and
remaining
again
points,
grouping according to the nearest
and again
distance
grouping
is done.
according
We
to the
get the
nearest
same group
distance is
as
done. We
previous
get the
one.
same group
Again
as previous one.
recalculation is performed
Again
for
recalculation
the
is
groups,
performed for the
and
groups,
we notice there is no change
and
and
we
centroid
notice there
remains
is
the
no
same.
change and centroid remains the
Similarly,
same.
round 3 to 10, the centroid will
Similarly,
not
round
change
3
further
to
after
10, the
round 2
centroid
because
will
the
not
assignment
change
of
further
point
after
to
round
clusters
2
and
because the
the
assignment of
recalculation
point to
centroid
clusters and the recalculation
stabilizes.
of
This
centroid
process is repeated and
stabilizes. This process
as a
is
result we
repeated,
will
and
see
we,
the
as a
centroid
result,
will
we will
not
see
change.
the
Final
centroid will
output,
not change.
cluster 1,
Final
2, 4, 2
output,
and cluster 2
cluster
is
1,
10,
2,
12,
4, 2
20,
and the
30,
cluster
11,
2 is
25.
10, 12, 20,
The
30, 11,
algorithm
25.
converges after
The
2 rounds with
algorithm
no change in
converges
centroids
after
after
2
that.
rounds
The
with
final
no change in
clusters
centroids
are.
after that. The final clusters are.
This result suggests that the point close
This
to 2
result
are
suggests
grouped
that the
together in
point
one
close
cluster
to
and
2
the
are
remaining
grouped
point
together
from
in
the
one
second
cluster, and
cluster.
the
Basically
remaining
what
point
cluster
from
is
the
grouping.
second cluster.
So we have
Basically, what
done
cluster is grouping.
of
So we have
these points
done
according
grouping
to the
of
nearest
these
distance.
points according to the
Next
nearest
question, that is
distance.
question 5. Explain
Next
the key
question,
difference
that is
between
question
k-mean
5.
clustering
Explain the
and
key difference
hierarchical
between k-mean clustering
algorithms.
and hierarchical
What
clustering
are
algorithms.
what are the
What
advantages of
are
hierarchical
what are the
clustering over
advantages of
k-means when
hierarchical
visualizing
clustering
cluster
over
relations?
k-means when
Key
visualizing
difference
cluster
between
relationship?
k-mean clustering
Key
and
difference
hierarchical
between
clustering.
k-mean clustering
Types of
and
clustering.
hierarchical
K-mean.
clustering.
A
Types of
partitional
clustering.
clustering
K-mean.
algorithm
A
which divides the
partitional
data
clustering
into a
algorithm
predefined
which
number of
divides the
clusters.
data
The
into
number of
predefined
clusters
number of
is
clusters. The
specified
number of
beforehand.
clusters is
Hierarchical
specified
clustering
beforehand.
algorithm which
Hierarchical
creates a
clustering
tree-like structure
algorithm
that
which
show
creates a
how
tree-like
clusters are
structure
formed at
that show
different
how
level of
clusters are formed at
granularity.
different level of
It can be
granularity.
agglomerative or
It
divisive.
can be agglomerative or divisive.
Input requirements. In k-mean require the
Input
number of
requirements. In
clusters
k-mean
to be
require the number of
specified before running the
clusters to
algorithm,
be specified
and
before
in
running the
hierarchical
algorithm,
it does not
and
require the
in
cluster
hierarchical it
to
does
be
not require
specified
the
in
cluster
advance. It
to be
produces a
specified in advance.
dendrogram that
It
can be
produces
cut
a
at any level
dendrogram that can be cut
to
at
get
any
a
level
desired number of clusters.
to get a
Cluster
desired
formation.
number of
In
clusters.
k-mean
Cluster
points are
formation. In
assigned to
k-mean
clusters
points are
based on proximity
assigned
to
to
the
clusters
cluster
based on
centroid.
proximity to the
The centroid
cluster
of each cluster
centroid.
is
The centroid
recalculated
of each cluster
iteratively
is
until
recalculated
convergence. We have just
iteratively
seen the
until
example of
convergence. We
k-mean.
have
You can
just seen the
understand
example of k-mean. You can
from
understand
this. Hierarchical at
from
each step
this.
clusters are either
Hierarchical
merged,
at each step
agglomerative or
clusters are
split,
either merged, agglomerative or split,
based on some distances
divisive,
metric
based on
like
some
Euclidean
distances
distance,
metric like
cosine similarity.
Euclidean distance, cosine similarity.
Scalability. In k-mean typically more
Scalability. In k-mean
for
typically
large
more
data set
scalable for large data set because it works with an iterative approach and does not compute all pairwise distances.
In hierarchical
Generally,
lower,
in hierarchical
slower
generally
and
lower,
less scalable for large
slower
data set
and
as
less
it
scalable
computes
for
and
large
maintains
datasets
or
as it
distance
computes
matrix
and
for all
maintains or
points,
distance
making
matrix
it
for all
computationally
points,
expensive
making it
for
computationally
large
expensive
datasets.
for
Cluster
large
shape. In
datasets.
K means
Cluster
assume
shape.
cluster to be
In K
roughly
means
spherical
assume
or
cluster to be
circular in
roughly
shape as it
spherical or
uses
circular
centroids
in
and
shape as it
minimizes
uses centroids and
intra-cluster
minimizes
variance.
intra-cluster
Hierarchical can handle
variance.
clusters of
Hierarchical
arbitrary
can handle
shape
clusters
because it
of
does not rely
arbitrary
on
shape
centroids.
because it does
It
not
group
rely on
data
centroids.
based on
It
distance
group
metrics.
data based on
Handling
distance
of
metrics.
outliers.
Handling
K-means
of
sensitive
outliers.
to outliers
K-means
as they can
sensitive
distort
to
the
outliers as
calculation
they
point
can distort the
of the centroids.
calculation point
Hierarchical less
of
sensitive
the
to
centroids.
outliers,
Hierarchical less
especially in
sensitive to
agglomerative
outliers,
hierarchical
especially
clustering.
in agglomerative hierarchical clustering.
Here are many more differences
Here are
like
many more
result
differences preferences like result representation, sensitivity to initialization, computational complexity, and the last is
Now we'll move to the advantages of
Now we'll
hierarchical
move to the
clustering over
advantages of
K-means in
hierarchical
visualizing
clustering over
cluster
K-means
relationship.
in
No
visualizing
need to
cluster
specify
relationship.
the number of
No need to
clusters. Hierarchical
specify the
clusters
number
does
of
not require
clusters.
the number of
Hierarchical
clusters
clusters
to
does
be
not require the
set
number of clusters
beforehand.
to be
Dendrogram
set beforehand.
representation. The tree structure
Dendrogram
of the hierarchical
representation. The tree
clustering
structure of the
dendrogram
hierarchical
allows
clustering
users to
dendrogram
visually inspect how
allow
clusters
users
are
to
formed
visually
and how
inspect
data
how
points are
clusters
grouped
are
at
formed
various
and how
levels.
data points are grouped at various
Visualization of
levels.
nested cluster.
Visualization of
Hierarchical
nested
clustering
cluster.
reveals the nested
Hierarchical
structure
clustering
of
reveals
data,
the
making
nested
it
structure
easier to
of
understand
data,
how
making
small
it easier
clusters
to
combine
understand
into larger
how
ones.
small cluster combine into larger
Flexibility
ones.
in cutting the dendrogram.
Flexibility
Users
in
can choose
cutting the
any level of
dendrogram.
dendrogram
Users
to
can
cut
choose
and
any level of
define the number
dendrogram
of
to cut
clusters,
and define the
allowing
number
for
of
an
clusters,
initiative
allowing for an
exploration
initiative
of cluster sizes.
exploration
In
of cluster sizes.
identification of
In
cluster relationship.
identification
The
of cluster
dendrogram
relationship.
helps
The dendrogram helps
identify the relationship between clusters
identify
such
the
as which
relationship
clusters are
between
more
clusters
similar
such
and
as
which
which
one are more
clusters are more
distinct,
similar
providing
and which one
deeper
are more
insights into
distinct,
the data.
providing deeper insights into the
Interpretability
data.
of cluster merging. The
Interpretability of
process
cluster
of
merging. The
cluster
process of
merging
cluster
in
merging
hierarchical
or
clustering
splitting
can
in
often be
hierarchical
understood
clustering can often be understood
initiatively, making it easier to interpret how
initiatively,
different groups
making it
relate
easier
to
to
each other.
interpret how different
No
groups
need for
relate to each other.
predefined centroids.
No need
Unlike
for
K-means,
predefined centroids.
hierarchical
Unlike
clustering
K-means,
does not rely on
hierarchical
a
clustering
fact
does
that
not rely
centroid-based
on a
approach which
fact
can
that centroid-based
sometimes
approach
lead to
which can
misleading cluster shapes. The
sometimes lead
approach
to
can
misleading
handle
cluster
complex
shapes. The approach can handle complex
structures
cluster
better.
structures better.
Sensitive to small variation.
Sensitive to small variation.
Captures even
Hierarchical
small
clustering
variation in the data
captures
by
even
creating
small
clusters
variation in
at
the data
different
by
levels. This is
creating
useful
clusters
when
at different levels.
fine-grained
This is
cluster
useful
differences
when
are important for
fine-grained cluster
analysis.
differences are important for
Works
analysis.
well with small dataset. For
Works
small
well
dataset,
with small
hierarchical
dataset. For
clustering
small
provides a
dataset,
thorough
hierarchical
exploration
clustering
of the
provides
data,
a thorough
making it
exploration
a
of the
good
data,
choice when the
making
relationship
it
between
a
the
good
data
choice when
points
the relationship between the data points
need to be examined in detail.
need to
In
be
summary,
examined in
hierarchical
detail.
clustering offers a
In
more
summary,
flexible
hierarchical
and
clustering
visual
offers a
approach to
more
clustering,
flexible and
especially when
visual approach
relationship
to
between
clustering,
clusters at
especially when
different levels
relationship between
are
clusters
important
at
for
different
analysis.
levels are
K meanwhile
important for
faster
analysis.
and more
K
scalable for
meanwhile
large
faster
dataset
and
does
more
not offer
scalable
the
for
same
large
depth of
dataset does
insight
not
into
offer
the
the same depth of
hierarchical
insight into
structure
the
of the
hierarchical
data.
structure
Thank you. I
of the
hope you
data.
understand the topic
Thank
and
you.
like the
I
video.
hope you understand the topic and like the video.